I hope you're all doing well and having a great day. I'm Mr. Ish. Thank you for joining me. We're looking here at another video solving a differential equation, DE. Except here we're looking at the procedure of separation of variables. That's a way of solving a differential equation. Previously in another video we looked at direct integration route. Here we're looking at separation of variables. Remember, solving a differential equation means you're given a differential equation. You're trying to eliminate the derivatives in that equation to determine what was the function for which that differential equation is true. So at the end you're coming up with a function or an expression which develops and demonstrates a relationship between x and y, and there is no derivative in there. These are the type of differential equations where you have an equation here in terms of x and y, you have a derivative involved, and you're going to separate the variables. These are again all first order. A good way over here to just give you the general idea of this form of procedure, this style of procedure for solving a differential equation, is by means of an example. Let our first example be this. We have something which is dy over dx is equal to 2x over y plus 2. You see over here we have in this differential equation, this right here is also same thing as y prime is equal to all of this. You have a derivative, you have x and y variable, but you see you have to separate it. You have something which looks like this. How can you solve this differential equation? That is, how can you come up with a function for which this differential equation is true? Well, how about you separate the variables, cross multiply. You'll have y plus 2, and then you have dy over dx is equal to 2x. What you can do is an integration procedure on both sides. You can integrate this, you can integrate this. And let me rewrite this out cleanly. Y plus 2, you have a dy over dx is equal to integral 2x dx. You see, we separated the variables and now we'll integrate those variables. These polynomial integrands over here are easy to do their antiderivatives. It's not hard. You're going to generate a y squared over 2 plus 2y, and then from here, don't forget the constant of integration. You'll have 2x squared over 2 plus c. Simplify it all. You'll have y squared over 2 plus 2y is equal to x squared plus c. This represents the expression or the equation for which this first order differential equation is true. And if you're given this, you have to demonstrate the function or the equation, then this right here is your answer. Imagine this is the differential equation you're given, the first order differential equation, because you have everything here with regards to first order. You have to find the equation or the expression for which this is true. How will you do it? You have to separate the variables. You have something which looks like this in terms of x and y, but you separate them. How about you cross multiply this down? You'll have 1 over 1 plus y, and then you have this dy over dx is equal to 1 over x minus 2. From this step here, just do the integration of both of these separately. You have a dy over dx with respect to dx of this right here, 1 over 1 plus y. You're integrating that is equal to the integral of this dx over x minus 2. It has the elements of the integration, as you know from the previous video on solving differential equations, except here you separate the variables first. Look right here, this cancels out. You end up seeing just here dy over 1 plus y is equal to integral dx over x minus 2. These are easy. This is going to bring here natural log 1 plus y is equal to here natural log x minus 2 plus c. You can hold this right here as your final answer, or you can take this to one step further and eliminate and get some meaning in here with regards to this constant of integration. Let natural log of a equals c, and see how this plays out right here. This little substitution is a neat trick. You have this as your answer. You can get rid of the natural logs too by means of this little trick. Natural log 1 plus y is equal to a natural log x minus 2 plus natural log of a. You can combine this under a common log. You have natural log 1 plus y is equal to a natural log here a times x minus 2. The sum of logs is equal to their product. You can basically eliminate the natural logs over here. You can. There's nothing wrong with you doing that. 1 plus y is equal to ax minus 2a. And this can be your final answer if you want. You've eliminated the derivative. You've done this procedure of separation of variables, and you've brought in a constant, except here instead of c we used a by means of this little substitution. You could have either kept your answer right over here if you wanted, or by means of this substitution you take it to this form right over here. They're both equivalent and they're both right. You could have even taken this one step further and isolated the a. you could have said 1 plus y is equal to a into x minus 2, and that would be fine as well. Let's look right here. We have a differential equation. dy over dx is equal to 4 plus x times y plus 3. How can you go about using the separation of variables to solve this first order differential equation? How about you take this and you bring it on the other side? You'll have 1 over y plus 3 dy over dx is equal to 4 plus x. Now how about you integrate all of this? Bring in the integral sign. You'll have a 1 over y plus 3 dy over dx is equal to integral 4 plus x dx. These cancel out right here, and you're doing the integral of that and integral of this. This will bring the natural log, but this right here is polynomial, it's not hard. You'll have here a natural log y plus 3 is equal to the antiderivative of this, 4x plus x squared over 2 plus c. Now here you cannot do a substitution here to get rid of the natural log, because you can only do that trick I showed you in the previous question. When you have natural logs across, they would remove by the end of this entire procedure. So you would have to keep this as your final answer. Natural log y plus 3 is equal to 4x plus x squared over 2 plus c, and that would be your answer. Let's look at this one right over here. We have cosecant x dy over dx is equal to y squared plus 1. A good idea would be just parenthesize that and look at that as a single unit. Separate the variables. Take the cosecant x on this side, take this y squared plus 1 on this side. You'll have 1 over y squared plus 1, and then you're looking at a dy over dx is equal to 1 over cosecant x. But 1 over cosecant x can be written as sine x, right? You're looking at 1 over y squared plus 1, and then dy over dx is equal to sine x. You can do a good integral over here and take everything to completion now that you've separated the variables, and that would play out as this. You're looking at 1 over y squared plus 1 dy over dx, and then dx is equal to integral of sine x dx. The integral of sine x, is a minus cosine x plus c. So that part is done. But what about here? You want to do a trigonometric substitution, or do you want to just bring in the arctan? I can just bring in the arctan y. And that right there will represent your function for which this differential equation here is true. This entire differential equation would hold true for that expression over there, and it would be good. There's no need to do a trigonometric substitution. You do have something which looks like a squared plus x squared, and you can do those series of substitutions, bringing in the tan theta and the secant square theta d theta, but there's no need to do it. You'll end up right there anyways. That answer right there has been completed for you. We have this one right here, xy plus y. How can we do this? We have to separate the variables, rewrite them by isolating the y. You have here x plus 1. Now bring the y on the other side. You'll have 1 over y dy dx is equal to x plus 1. Now bring in the integral sign. You'll have 1 over y dy dx is equal to integral of this x plus 1 dx. Integrate this. You're getting a natural log over here, but over here you're getting an x squared over 2 plus x plus c, and this can very well represent your answer, the function, the equation for which this first order differential equation should hold true, and the answer should be right. Maybe we can do one more question and just look at this right here. Squeeze in this last question. Cosine x dy over dx is equal to 2e to the y. We have to find the function or the equation for which this differential equation holds true. How about we cross multiply and bring things over onto the other side? We have here 1 over e to the y dy dx is equal to, you'll have 2 over cosine x. I've cross multiplied cosine x and e to the y. You can rewrite this, e to the minus y dy dx is equal to 2 secant x. Now bring in the integral sign. You'll have e to the minus y dy dx is equal to 2 integral secant x dx. I'm just keeping the 2 outside. The antiderivatives of everything you see over here are not difficult. This, in terms of antiderivative, is going to be minus e to the minus y. With this you have a 2, and then you're going to bring in the natural log, and then secant x plus tan x, and then plus c. You can hold this as your final answer if you want, or you can write this in a better way. Get rid of that negative exponent. You can do minus 1 over e to the y is equal to 2 natural log, and then secant x plus tan x plus c, and that right there can represent a good final answer. The function or the equation for which this differential equation, the first order differential equation will be true, and that right there is your answer. Remember, in this we've been solving, in this particular video, differential equations which are first order by means of this technique, a generalized technique, separation of variables. It very much has the addition of the previous technique, the direct integration route, but you have to separate the variables first, because in the previous video we only saw equations here in terms of x. Here you're seeing the x and y, you separate them, then you bring in the integral procedure, and then that takes you to your final answer. And that's it for this particular video. You all have a great day. Thank you. Bye.